Section 9.1, Sequences and their notations. A video game company launches an exciting new advertising campaign. They predict the number of online visits to their website or hits will double each day. The model they are using shows 2 hits the first day, 4 hits the second day, 8 hits the third day, and so on. So if we take a look at table 1, here's the days, 1, 2, 3, 4, 5, and so on. And then the hits go from 2, 4, 8, 16, 32. Now, if their models continue, how many hits will there be at the end of the month? Now, to answer this question, we'll first need to know how to determine a list of numbers written in a specific order. In this section, we will explore these kinds of ordered lists. Writing the terms of a sequence defined by an explicit formula. One way to describe an ordered list of numbers is as a sequence. A sequence is a function whose domain is a subset of the counting numbers. The sequence established by the number of hits on the website is 2, 4, 8, 16, 32, and so on. Now, the 3 dots is called the ellipsis, and the ellipsis indicates that the sequence continues indefinitely. Each number in the sequence is called a term. The first 5 terms of the sequence are 2, 4, 8, 16, and 32. Now, listing all of the terms for a sequence can be cumbersome. For example, finding the number of hits on the website at the end of the month will require listing out as many as 31 terms. A more efficient way to determine a specific term is by writing a formula to define the sequence. Now, one type of formula is an explicit formula, which defines the terms of a sequence using their position in the sequence. Explicit formulas are helpful if we want to find a specific term of a sequence without finding all of the previous terms. We can use the formula to find the nth term of the sequence, where n is any positive number. In our example, each number in the sequence is double the previous number. So we can use powers of 2 to write a formula for the nth term. And so 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. 2 to the fourth power is 16. 2 to the fifth power is 32. Now again, the first term of the sequence is 2 to the first power. The first term being 1 is going to give us 2 to the 1 power. The second term again is 2 to the second power is 4. The third term is 2 to the third power, which is equal to 8, and so on. Now the nth term of this sequence can be found by raising 2 to the nth power, so that would be 2 to the nth power. So an explicit formula for a sequence is named by a lowercase letter a, b, or c with the subscript n. So the explicit formula for this sequence is a subscript n, which is equal to 2 to the nth power. Now that we have a formula for the nth term of the sequence, we can answer the question posed at the beginning of this section. We were asked to find the number of hits at the end of the month, which will take to be 31 days. Now, to find the number of hits on the last day of the month, we need to find the 31st term of the sequence. So we will substitute 31 for n in the formula. Now, if the doubling trend continues, the company will get 2,147,483,648 hits on the last day of the month, and that is over 2.1 billion hits. Now, the huge number is probably a little unrealistic because it does not take consumer interest and competition into account. It does, however, give the company a starting point from which to consider business decisions. So now let's check with our calculator 2 to the 31st power. So if we put 2 to the 31st power, then it's going to give us the result that we've seen here. Again, 2,147,483,648 hits. Now, another way to represent the sequence is by using a table. The first 5 terms of the sequence and the nth term of the sequence are shown in table 2. So the first 5 terms of the sequence, so when n is equal to 1, we get 2. When n was equal to 2, 2 squared, that gave us 4. When n was equal to 3 to the 3rd power gave us 8. When n was 4 to the 4th power gives us 16. When n was equal to 5 to the 5th power gives us 32. And then when n is equal to n, that is 2 to the nth power. Now, we can also graph this. So when we graph the table, we have an ordered pair. So here we have 1 and then 2. There's the ordered pair. The second one is 2, 4. The third one is 3, 8. We have 4, 16, and then 5, 32. So you can see what's happening if we connected these dots. Now, we can write this particular sequence as the following. We have these braces with 2, 4, 8, 16, 32, ... 2 to the nth power, which would then be ... which is the ellipsis. Now, a sequence that continues indefinitely is called an infinite sequence. The domain of an infinite sequence is the set of all counting numbers. So in this case, because the ellipsis at the end, this is a continuation, which tells us this is an infinite sequence. Now, if we consider only the first 10 terms of the sequence, we could write the following: 2, 4, 8, 16, 32, and it ends at 1024. Because it ends here and not the ellipsis, then we would call this sequence a finite sequence because it does not continue indefinitely.